Hello and welcome all students. How are you? Students, in the previous session, we discussed about the kinetic theory of gases and ideal gas laws and ideal gas equation. In the today's session, I will tell you about the van der Waals gas equation or the real gas equation. We discussed about the ideal gas. Now it is time to discuss about the real gas. What is the real gas? And what is the difference between ideal and real gas? And also we will discuss about the conversion of gas into liquid and the factors which are involved in this, like critical volume, critical pressure, critical temperature. These parameters Dr. Andrew's experiment, we will discuss all of them in today's session. So come, let us study about these all in today's session. Behavior of real gas. In the last class we discussed about the van der Waals gas or the real gas. Now it is time to discuss about their behavior. And moreover, we shall discuss about the deviation from the ideal gas behavior. We studied about the ideal gas law, which is PV is equals to nRT, but it is not necessarily true that all the gases follow ideal gas equation at all given conditions. So the gas which obey all gas laws and follow the ideal gas equation PV is equals to nRT under all conditions of temperature and pressure is called as ideal gas or perfect gas, and this follow ideal gas equation PV is equals to nRT. But there is no gas that obey ideal gas equation under all conditions of temperature and pressure. Means if you suppose that there should be a gas which should follow all the gas laws and moreover ideal gas equation under all pressure and temperature, then such gas in real life do not exist. So the basically concept of the entire concept of ideal gas is completely theoretical, or you can say it is hypothetical, which is imaginary. Moreover, I would like to add in this that ideal gas behavior, it can be observed, or very close to the ideal gas behavior can be observed only at high temperature and low pressure. See, basically, you know what happens in the ideal gas concept, we assume that there is no force of attraction between molecules, but actually it does exist. So in order to reach the ideal behavior, if you want to go to the close to the ideal behavior, then there should be less force of attraction between molecules, which is possible at high temperature and low pressure. This is the curve. This is the PV curve, pressure volume curve for real gas and ideal gas. There is a difference in the curve of real gas and ideal gas. Also their slopes are also different. Now what happens at high pressure? At high pressure, measured volume of hydrogen is found greater than the calculated volume of hydrogen, or you can say calculated value is the ideal behavior. Suppose you have hydrogen gas at some condition. Now according to the ideal gas law, there should be some certain volume of this hydrogen gas. But if the measured volume of this hydrogen is much higher than the calculated value, then this is called as deviation. But at low pressure, measured volume of hydrogen is almost somewhat similar to the calculated volume of hydrogen. So pressure should be low. In order to approach the ideal condition, now it is proved that pressure should be low. Now we will plot a curve between PV and P. See, at a constant temperature, this curve is plotted for constant temperature. Students, for the constant temperature, this is the curve for ideal gas. And most of the real gases, they show initial dip in the graph. See, for this ideal gas, the value of compressibility factor Z is 1. For the real gas, sometimes it is greater than 1 and sometimes it is lesser than 1. For most of the gases, like I said, for most of the real gases, initially value of Z is lesser than 1. Means there is an initial dip in the value, and after certain time it becomes 1 and more than 1. Although for hydrogen and helium, value of Z is greater than 1 right from the beginning. For ideal gas, this graph is straight with parallel to the x-axis. This graph is of ideal gas, which is a straight line and parallel to the x-axis. But for the real gas, this graph is actually not a straight line. There is a significant deviation observed from above two type of curves in the real gases. For hydrogen and helium, as the pressure increases, the value of PV always increases. So with the increase in pressure, their pressure into volume value, PV value, always increases. But for the other gases like CO2, CH4, ammonia, SO2, O2, and many more other gases, the curve first decreases, which is negative deviation. Negative deviation means Z is less than 1, and then increases, which is positive deviation, means Z is greater than 1. See, whenever we use the term deviation, it means it is deviated from the ideal behavior. But when it deviates in the positive direction, means more, it is positive deviation. And when it deviates towards the negative direction, negative value, it is negative deviation. So the real gases do not follow the ideal gas equation perfectly under all conditions. They might follow under some certain conditions, but not all conditions, right? Now we will discuss the measurement of this deviation. If the gases are deviated from the ideal behavior, we have to measure how much is the deviation. Now by comparing the observed molar volume and the real molar volume, one is the observed, which is real molar volume, and the another is the ideal molar volume, which should be as a function of ideal gas. I mean to say, whatever the volume of gaseous system is having in the given condition, in compare to the volume we suppose in the same conditions according to the ideal gas law, that is called as measurement of deviation. Now as a function of pressure at constant temperature, deviation can be measured by this value. Vm is nRT upon P. So the ratio of molar volume, this is important students, the ratio of molar volume of a real gas to the molar volume of an ideal or the perfect gas is called as compressibility factor Z. So Z is V real upon V ideal. Now if suppose any gas is ideal, for any ideal gas, the value of Z will be 1, because here PV is equals to nRT. So the value of Z is 1. In other terms, you can also say that V real is now equal to V ideal. So this is the gas which will occupy exactly 22.4 liter volume at STP. This gas will occupy exactly 22.4 liter volume at STP. And if in case this gas is real gas, then definitely Z is not less than equal to 1. See, when Z is not equal to 1, it has two meanings. Either it will be greater than 1 or it will be lesser than 1. Now it has two meanings. Z could be greater than 1, which we call positive deviation, and Z could be lesser than 1, we call negative deviation. Now we shall discuss both of them one after one. So thus in case of real gas, the value of Z can be less than 1 or it could be greater than 1. When Z is less than 1, it refers to the negative deviation. What do you mean by negative deviation? Negative means less, means lesser. So it refers to the negative deviation. It implies that the gas is more compressible than the expected from ideal behavior. It is more compressible than comparison to the ideal gas. That is the reason why its volume is less. Volume of real gas is less. You know what? You must be knowing that 1 mole ideal gas occupy 22.4 liter volume at STP. Now this gas, for which Z is less than 1, it will occupy less than 22.4 liter volume at STP. This gas will occupy less than 22.4 liter volume at STP. While on the other hand, if Z is greater than 1, it refers to the positive deviation and it implies that the gas is less compressible. If compressibility is less, volume will be more. So this will occupy more than 22.4 liter volume at STP. Now, what do you think? The extent of deviation is same for all gases. The quantity or the extent in which gas is deviated from the ideal behavior, do you really think that this extent of the deviation is same for all? No, the answer is no. Actually, the extent of deviation, it depends upon the nature of gas. That is the reason why we have different curves. Those gases like CO2, CH4, N2, etc., which are more compressible at low pressure and less compressible at high pressure. So at low pressure they show negative deviation, while the same gases will show positive deviation at comparatively high pressure. But surprisingly, hydrogen and helium, they just show positive deviation only at all pressures right from the beginning. Now there is a term which comes in front of you, is the boil temperature. We represent the boil temperature by symbol TB. So what is boil temperature? It is the temperature at which behavior of the gas is very close to the ideal behavior for a wide range of pressure, and it is known as boil temperature. It is known as Boyle's temperature, TB. The Boyle's temperature is called as A upon RB. So if you have any gas at boil temperature, then at this condition it will behave as a ideal gas. So the temperature at which behavior of gas is very close to the ideal behavior. You know what, when we say close to the ideal behavior, what do we mean by saying this? We mean to say that at this temperature gases follow ideal gas law, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, Graham's law, Dalton's law. They follow these rules. Now what is the cause of deviation from ideal gas behavior? If I ask why gas deviates from the ideal behavior, so the cause of deviation from the ideal behavior, it is just because of the two faulty assumptions which we considered in the KTG. When we studied the KTG, we gave the postulates of KTG. By mistake, we did the two faulty assumptions. So we have to make two corrections. First faulty assumption was, we suppose that actual volume of gas molecule is negligible as compared to the total volume of gas, which is the equal to the volume of container. In easy words, I say in first faulty assumption, what mistake we did, we considered that the volume of molecule itself, the volume of the gas molecule itself is negligible in comparison to the volume of container, which is actually not true. And also the other faulty assumption was, intermolecular attractions are not present in gas molecule. This is wrong actually. See, now we realize that intermolecular force of attraction, it could be high, very high, or could be low, could be very low, but it could not be zero. But in KTG we supposed it. So at the high pressure and at the low temperature, if you reverse the condition, I told you few minutes back that at low pressure and high temperature, gases show ideal behavior. They found somewhat very close to the ideal behavior. Now what will happen if we reverse the condition? Instead of low pressure, if we have high pressure, and instead of high temperature, suppose if we have low temperature, then in this case gas will started behaving like the real gas, right? So in order to correct these two faulty assumptions, we did two corrections. One is volume correction. Volume correction is what? We said that molecule of real gas possesses a definite volume, and this volume is not negligible in comparison to the volume of gas. So now the corrected volume is V minus B. We say that now corrected volume, or the new volume, is V minus B. What is B? B is the excluded volume. And this B is also called as van der Waals constant. And this is for 1 mole. If you consider this for n moles, it will be V minus NB. So this is the corrected volume. I would like to say this is corrected volume, right? The excluded volume B is 4 times the actual volume of the gas molecule. Means, do you understand what is the meaning of this? Whenever any gas molecule is in moving state, it actually occupy 4 times volume of its real volume in the moving state. Of course, in the still state, it will occupy the volume exactly like 1 time of the real volume. But in moving state, it occupies 4 times of the actual volume of the gas molecule. And this excluded volume B is calculated by this calculation. Now you consider bimolecular collision of the sphere with the radius is 2r. So this is the excluded volume, which is 4 times of the volume of the molecule. So this is the excluded volume. We calculated by the mathematics. 4 by 3 pi r cube, r is 2r. And by doing so, if we get it is 4 into volume of the one molecule. So 4 times of the volume occupied by one molecule is the excluded volume. And B is a constant called as van der Waals constant, and it depends upon the nature of gas. This is important. And its dimension is also very important. Dimension of V is equals to NB. Dimension of V is equals to NB. So the dimension of B will be V upon N. Now V is volume and N is mole. So you can call this liter per mole, or liter could also be expressed in the meter cube or the decimeter cube. So these are the different units of van der Waals constant B. Now we did another correction, that is the pressure correction. Why we need to perform the pressure correction? Because we did mistake, faulty assumption. We considered that the volume pressure of attraction between molecule is 0, which is actually not 0. It could be less, very less. It could be very low, but cannot be 0. So the intermolecular force of attraction between gas molecule are equal and opposite. So they cancel each other. But a gas molecule which is just going to strike the wall of the vessel or the container, it experiences an inward pull due to the imbalanced attractive force. And that is the reason why force of attraction is there. You see in this diagram, this particle, when it strikes the wall with the less momentum, because these other particles, they are constantly attracting this particle toward themselves. So now when this particle will go and strike the wall, it will strike with the less momentum, because this particle itself is being attracted by these particles. In this diagram, I've shown 3 other atoms, although there are plenty of them. So the observed pressure will be less than the ideal pressure, because when particle will collide to the container, wall of the container with a lesser momentum, it will exert less pressure. So then we did the pressure correction. The observed pressure is somewhat lesser than ideal pressure. So the attractive forces exerted on a single molecule about to strike the wall is directly proportional to the number of molecule per unit volume in the bulk of gas. Do you understood this? Let me tell you one more time. The attractive forces exerts on a single molecule which is about to strike the wall is directly proportional to the number of molecule present in per unit volume. More number of molecule will be there in per unit volume, more attraction they will create on the particle which is about to strike the container, and lesser will be the momentum, lesser will be the real pressure. So the number of molecule striking the wall is proportional to the number of molecule per unit volume. Greater number of molecule per unit volume, more density, more particle will collide to the wall. It is very obvious. So these factors are proportional to density. Population density means density of the particles or the number of molecules per unit volume. So P1 is directly proportional to the total attractive force. And what is this P1? This P1 is the corrected volume. Volume correction is proportional to density square, is proportional to 1 upon volume square. Then we placed a constant which is A, and this A is van der Waals constant again. And this also depends upon the nature of gas, like van der Waals constant B. So now finally the corrected pressure is P plus P, which is ideal pressure, plus A upon V square, observed pressure plus A upon V square. Now when you replace these two values in the ideal gas equation, you will find this value, P plus A upon V square into V minus B is equals to RT for 1 mole. Now if n moles are there, this will be the equation. And my dear students, this is called as van der Waals equation, or it is also called as real gas equation. What about the unit of A? Like we discussed the unit of B. Unit of A is atm into liter square upon mole square. This is the unit of A. And unit of B is liter per mole. These are very important. Examiner used to ask about this unit. What is the significance of A? This van der Waals constant A, it gives an idea of intermolecular force. Simply, we say that larger the value of A, larger is the intermolecular attraction of the gas. So I say that attraction is directly proportional to the van der Waals constant small a. Greater the value of small a, greater will be the attraction. Now the gases having higher value of A, they can be liquefied very easily, because if the value of A is high, of course their force of attraction is high. Force of attraction is high, conversion of gas into liquid is very easy. Significance of B. The van der Waals constant B, it represents the excluded volume, prohibited volume, which is 4 times the volume occupied by the gas molecule. Now the value of B remains constant over a wide range of temperature, because volume of gas molecule remain constant with temperature and pressure, which implies that gas molecules are incompressible. So the gas molecules are practically incompressible. This is explained by van der Waals constant B. Right. Now we will explain the behavior of real gas by van der Waals equation. Now what happens when pressure is low? See, when pressure is low, of course temperature is high. Under the above conditions, low pressure and high temperature, volume of gas is very high. See, when pressure is low, definitely volume will be high. Now if volume is high, then 1 upon V square is very small, and small values can be neglected. So P plus A upon V square, it could be called as just P instead of P upon plus A upon V square, as this value is very small. It could be neglected, and P plus A upon V square could be written as P. If you will written as P, if you will write it as a P, you will get the value of Z lesser than 1. Now at the moderate pressure, volume decreases. Definitely pressure increases. And if volume decreases, now this value, it cannot be neglected, because now volume is not very high. But yes, V is still large enough in comparison to the B. So now we will neglect V minus B and we will consider it almost V. So in this case, van der Waals equation, if you replace the value of Z becomes 1 minus A upon VRT. So in this case, value of Z is not less than 1, not only less than 1, it is A upon VRT less than 1. How much lesser than 1? A upon VRT lesser than 1, and Z is overall less than 1. This explains the negative deviation of real gas. In case of high pressure, volume is very small, so B cannot be neglected, but P is very high, so A upon V square can be neglected. Now we say that P plus A upon V square, it could be called as P, and if you replace this value here in this equation, you will get this equation. And now in this case, value of Z will be more than 1. And how much more than 1? PB upon RT more than 1. It is PB upon RT greater than 1. Now this explains why the value of Z becomes more than 1 at high pressure or the moderate pressure. So the volume of Z, which is compressibility factor, is always greater than 1 for hydrogen and helium. Why? Because of their very small size. In the beginning of this unit, I told you that for hydrogen and helium, Z is always greater than 1. It is because of their small size. Intermolecular force of attraction, they are negligible always. And if it is negligible, this is also negligible. This is negligible, value of Z is greater than 1. It is 1 plus Pb upon RT. So for them, Z always greater than 1 and increases as the pressure increases. That is the reason why for hydrogen and helium, Z is always greater than 1. There are some limitations of the van der Waals equation. The van der Waals equation is more accurate than ideal gas equation. It has deviation at high pressure and low temperature. Because of the van der Waals constant, A and B do not remain constant over the wide range of temperature and pressure. They also changes, and when they changes, this deviation is very high. So this is the difference between ideal gas and real gas. Ideal gas obey all the gas laws at all temperature and pressure. Real gas do not follow. The volume of molecule is negligible comparison to the total volume of gas, which is actually wrong. Attractive and repulsive forces do not exist, which is also wrong, faulty assumption. It actually does exist, and they all obey PV is equals to nRT. And interestingly, they are hypothetical. There is no such gas in this universe which could be called as ideal gas. While on the other hand, real gases, they obey gas laws only at very low pressure and high temperature. When these two conditions are met, pressure should be low and temperature should be high. They follow the gas laws. Their volume of molecule is not negligible. It is 4 times excluded volume. And the force of attraction between molecule, it do exist. But it do not exist particularly at high temperature and low pressure. But apart from different conditions, it do exist. And this is the real gas equation. We said van der Waals gas equation. Alright. Now Joule-Thomson effect. There were 2 scientists, Joule and Thomson. They studied and they found that when a gas is compressed and it is allowed to expand through a small hole, very small hole, cooling effect is observed and the temperature falls. This cooling effect is called as Joule-Thomson effect, or more specifically Joule-Thomson cooling. It was observed below a certain temperature, which is called as inversion temperature. This phenomenon happens below the certain temperature called as inversion temperature. So cooling effect is caused only during expansion if the temperature of the gas is less than inversion temperature. If the temperature of gas is greater than inversion temperature, then instead of cooling, heating effect take place, or you say negative Joule-Thomson effect. An expansion of gas at Ti means if the temperature of gas is exactly equal to the inversion temperature, it does not show any cooling or heating, means no Joule-Thomson effect is observed at the inversion temperature. And this is the value of inversion temperature, 2A upon RB. This is the value of inversion temperature where Joule-Thomson coefficient is 0, mu Jt. Mu Jt is the Joule-Thomson coefficient which is 0 at the inversion temperature. What is critical phenomenon and liquefaction of gas? We can convert the gas into liquid by applying low temperature and high pressure. Just reverse condition of the ideal. If you reverse the condition from the ideal behavior, which means temperature is low and pressure is high, then it is possible for us to convert gas into liquid, and that is called as liquefaction of gas. Molecules come nearer to each other and attractive forces operate, and due to this attraction between the gas molecule, it converts into liquid called as liquefaction. And there are 3 factors called as critical factors: critical temperature, critical pressure, and critical volume. What is critical temperature, TC? It is the temperature below which gas can be liquefied, but above which gas cannot be converted into liquid. While critical pressure is the pressure required to liquefy a gas at a critical temperature, because gas could be liquefied at the critical temperature but cannot above that. And critical volume is the volume occupied by 1 mole of the substance at the critical temperature condition. If PC and VC is there, then PC and TC is there, then volume is Vc. These are some constants value, critical constant value of the different gases given over here. And this is the order of liquefaction, decreasing order of the constant A. If lesser value of A, less attraction, less capability of liquefaction. And incompressibility of gas is what? The van der Waals constant B represents the excluded volume we already discussed. That is 4 times of the volume which is occupied by gas per mole. Value of B remain constant over a wide range of temperature and pressure. This implies that gas molecules are incompressible. So this is all we studied in this unit, my dear students. In the next class, we shall discuss about the numericals and questions which came in the previous year examination from this topic. I hope you liked today's lecture. Please keep coming and keep studying. Thank you.